Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our midterm review. So we stopped at, or we finished doing 13.4, which is basically about velocity, speed, and acceleration. And so now we're going to move on to doing something with functions of two variables and partial derivatives. And so here I'm actually going to look at some old exams maybe regarding these things. So oops. Let me go ahead and look at some of these stuff. Okay, let me just actually go to the homework and see if I can find something there. So 14.1 and 14.3. Okay. Something about contour maps as well. Oh, this was 14.1. And then this one's the 3. Then finding tangent plane is something for the next part. So this is basically just this. It's actually just these two. So something about contour maps and something about these things. Sketching domains. That sketching the graph. I don't think they're gonna make us do that. Sketching the graph is more or less just me writing some equation in order to, well, to get it, right? Matching functions with a graph. Allowance. Contour map. So this one here is basically okay, let me do something a bit with contour maps, but for the most part, I'm gonna focus on implicit differentiation with a function z. Yeah, let me do a bit of contour maps, just for a bit, at least with some computation. Okay, but here it's mostly just visuals, and then some reflecting and stuff like that. Okay, so let me go ahead and just go over some contour maps, and then we're gonna move on to, let me see the homework for the next one. Yeah, I'm still trying to like plan out how to do this. 14.3, which I think is the implicit differentiation one. Hopefully. And then I might make some general notes. These ones are determining the signs, so we're not gonna do that as much. We're probably just gonna do partial derivative. Actually, you know what? Let me just do it just in case. I just want to be super, super sure. Oof. So finding first partial derivatives here, finding first partial derivatives, finding first partial derivatives, implicit differentiation. Okay, let me do, that was, and then second partial derivatives, so that's another thing. That one's long. I would say finding second partial derivatives is long. And then, yeah, that should be it, hopefully. Okay, so let me just go ahead and start. Find and sketch the domain. More or less, this is a guessing game, so I'm gonna do that. I'm gonna do something a bit with contour maps though. So let me go ahead and try. Let's do like a couple of them. Okay, so here we have, okay, let me just go ahead. So here an example of a contour map that we can do, I guess, in this case. Okay, these are the, okay, let's move on to, how do I format my writing here? I think I did like, I don't know, I forgot. 13.4. So here I do like 14.1 and something about 14.3. So here, yes. So here's a contour map, right? Oh, some general, I'll go to the general tips later because I feel like we're going to learn that along the way. So here, first example is we're going to find an equation. Or actually, let's do it for all of them. Why not? Yeah, let's just do it for all of them. So here we want to find some equations of each cross section, right? How's that, how's that look like? Something like this from the homework, right? Okay, so here I'm being asked to find an equation for the cross section at z equals 1. So when we look at z equals 1, we're looking at this thing. And what do we notice? It's an equation of a circle in the xy plane when z is equal to 1. And so the equation of that cross section when z equals 1 is actually just a unit circle, and it has a radius of 4, so in this case 16. And then when z equals 3, it has a radius of, I think it was around like something 4.8, I don't know. Then it has an equation for the cross section at z equals 5. Where is that? Is this one? 5 is here, so it has 4, 5, 6, so 36. So again, this is really just finding the equation at each level curve. And then when z equals 7, so I look here again. When z equals 7, this is x squared plus y squared equals 64. And then when z equals 9, then that's just 144 is equal to x squared plus y squared. Right? So it's basically just finding at some level z, what's the equation of the curve in terms of x and y. Right? So that's the basic idea of it. And then more contour maps here. It's mostly just graphing at this point. So I'm not gonna bother, I guess. Draw a contour map. I don't think they're gonna tell us to do something like that. Find and sketch the domain. So it's really just, that one has to be something a bit easy. As long as we know what our elementary functions are, we should be good. Sketching domain, as long as we know what our bounds are, then we should be fine. Okay. Okay. Let me go ahead and move to, let me see. Okay. Let me move to 14.3 in this case, because there's not a lot of stuff here. Oh, so here, let's actually try this one. I want to determine the signs of the partial derivatives of some function f whose graph is shown below. So I actually want to try doing these parts. What are the signs of the partial derivatives? Yeah, this is something I think I also had difficulty with when I was, yes. So here, this point is basically 1, 2, and some z that I don't know. This is 1, 2. This is negative 1, 2. Okay. Oh, yeah, yeah. Okay, so here we're being asked, what is f of x or f sub x of 1, 2? So what is the change in x at this point? So as this is approaching positive x, they're a nice color here. As this is approaching positive x, it's actually going up, right? So this is increasing, right? So it means it has a positive derivative or positive slope. Oh, well, I did that. So the sign of this thing is positive, right? Okay, that's right. F sub y, as we're moving towards the y direction here, the positive y direction, here we're actually kind of going down, if you can see. So this is negative because it has a negative derivative, negative slope, right? We're going down here. Here we're going up, here we're going down. Okay, so it's stuff like that. And then we also had like some tricky parts here. What if we do f sub x of -1/2? So now we're looking at this point. Here, as we're approaching positive x, we're actually going a bit down here. So this is negative. So this is a negative sign. And then when we look at y, as it's approaching the y part, this is actually still negative. How do I know? I can see if I kind of put like a slope here or a tangent line, it's going down. Great. And here's the tricky part now. Here are the tricky parts at least. What if I have double or second derivatives? So here, what is f sub x of 1 and 2? Or -1 and 2 at least. So the way I check this is, well, first I get that slope at some x here. And then when you derive it, so this is the x. We're looking at this red arrow here. And then when you get the derivative of that, it's just going to be a positive, right? Yeah, it's just going to be some positive value. And I think, wait, why was this a positive again? I just remember this being positive, but then I actually kind of forgot why. Oh, concavity. Now I remember. If we take a deeper look into this, it's kind of like going like that, right? And so if we actually check the concavity, it's concave up. And so if it's concave up, we remember from calculus 1, if it's concave up, our derivative, our second derivative is greater than 0 if it's concave up. And so that means it's positive. Right? So this is positive. So here we're checking concavity. This is concave up of some function. And then we look at fyy of -1 and 2. So again, here we still check its concavity. So fyy of this point is, so f sub y is this, right? Which is negative. But then if you look at this is now concave down. And so it's still a negative, right? So here, if you can kind of see this, it's kind of like it's going down-ish, right? When it's concave down, it's negative. So this is concavity down, or concave down, doesn't matter. So here, when we're doing the same things here, it's actually, we're just checking its concavity. And then lastly, when we do something a bit unusual, what if we get fxy was that? So now we're getting a bit more tricky here because even I can't solve this at first try. So when I look at this point, I look at my I mean my y, right? So my y's behaving is going down, which is negative, right? F sub y is negative. Now when I take its derivative again in terms of x, well, here what happens is, what if I move this thing to the x direction? What is it gonna be? So if I keep on moving it to the x direction, I'm gonna get this, 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 right? Is it getting steeper or not? And here it's actually not getting steeper. And so I think that might be, yeah, that's positive because it's not getting steeper, right? So the idea here is move to x direction and see if like the behavior of that tangent line, if it gets steeper. And the moment it gets steeper, then we know it's negative, depending on the direction it once was, right? Now, if I look at, let's say, f x y of negative 1 over 2, 1 and 2, here I look at this point, negative 1, 2. And so what is this? So I analyze, I look at my y. My y is going down. If I move it towards the x direction, it's still going down. It's actually getting worse. So if it's actually getting steeper in this case, so this is negative, right? Because as I move it to the x direction at least once, it's going down, see? So as it moves to the x direction, it basically gets steeper. Right? So it's one of these things where we just try to analyze this stuff. But yeah, that's the idea of that. Okay. And then we try to find first partial derivatives of a function. So let's try doing that. Because I think that is something that is key in the exam. So let me just copy this. If I can do one of them, then I don't need to do the others. Because I feel like I'm just gonna get annoyed when I do some algebra here. Oh, what the? Okay. So that's the homework question, which was find the first partial derivatives. So what this is saying when we're looking at this, it's basically f sub x and f sub y, right? So f sub x here is we're treating x as the variable. This becomes 6x to the 5th. This becomes 6y to the 9th. Then we have f sub y. Here we're treating x as some constant. So this is 6x. And then this is 54, right? Because I bring down my 9. So 54 x y to the 8th. Nice, done. As simple as that. Okay, I'm not gonna get into the complicated thing anymore. Okay, find first partial derivatives, find first partial derivatives, find first. Okay, let's do one for a a three variable function. Let's try one of these. So basically, okay, let me do one here. So not much. Okay. So here we treat x is variable. Here we say y is variable. So it depends on which one's at the bottom. That's what the variable is. The rest are constant. So here, what if we have a three variable function? What is that? Well, we need to find, so here we need to find f sub x, f sub y, f sub z. That's what we need to find. And then we treat the rest as constants. So here we have f sub x. We take the derivative 7, x sine y minus, oh shoot, I remember this being long. This is 7 sine y minus z. Or actually, no, I don't think this is long. Why? Because I just treat 7 and this sine function as some number. So if I take the derivative of x, that's just that. F sub y here is when I treat my y as the variable, everything else is a constant. So I leave my 7x alone. This sine, I make it a cosine. This one gives me y minus z. And then I take a chain rule of this. So here I get a 0, I get 1. So I'm actually just left with that. Then lastly, I do an f of z. So here again, I just do the same thing. Z is a variable, everything else is our numbers, 7x. Take chain rule. And then here we say we have a negative, right? Y is a number, x is a number, that's 0, and then minus 7x cosine y minus z. And there we have it. Then we have some stuff again and again. Oh. And then here we find the indicated partial derivative. So I think this is another thing that we can try to do. So instead of just getting their partial derivatives with respect to some variable, we could also try to find the number. Or in other words, the slope of that tangent line with respect to something. So here we find f sub y, because that's what it wants us to do. Here we treat y as a variable. So x is a number here. So the derivative of this thing, well, we just do some chain rule here. Or product rule, I mean. So product rule, just setting it up. Right? And then here we say, okay, this is sine negative 1 xy. This is y. Oh, but then we take the derivative of that thing, which I think was 1 over square root 1 plus xy squared. And then just an xy chain rule. See if I got that one. Because I feel like definitely I forgot that one. Those were derivative techniques I haven't seen in a while. Quickly check what that was. Oh, it was a square root, my bad. And it was a minus. So what I did was inverse tan, not inverse sine. All right, so it's one of those things where I just totally forgot how to do it. So here we say this is square root. This is minus, right? This is xy prime. Here we treat, again, y. So this is just x, right? So we say this is x. X. We multiply it to here, so it's actually just xy. And we're done. Oh, I'm kidding. We're not yet done. Now we have to plug in everything here. So if I want, oops. So now the plugging in part is this. 3 times 1 over 6. 3 over 6, 1/2. Inverse of 1/2. And then this is xy. Xy is, so I'm multiplying it again. This is 1/2. So 1 over 2 of this thing, which is 1/2 of this thing, right? And so this is 1/4, right? This is this 3/4. I think this was the, I remember doing something like this. This was a 2, actually. So this was square root of 3 over 4. This is square root of 3 over 2. This was square root of 3. If I remembered correctly. And from there, I just needed to find what inverse sine of 1/2 was. And if I'll use my calculator. 0.52, I don't know what that number is. By 6-ish? Oh, it is by 6. Yes. And I get this thing. Now, another way I could have rewritten this was I could say this is square root 3 square root 3. This gives me this. Multiply it by 2, I get 6. I get 2. So I get 2 square root 3 plus pi over 6, which I think is the simplification of that whole thing. So that's the slope of that line. Okay, let's do some implicit differentiation. This is what I'm going to focus on because I know this is going to be part of the test. And we're going to do it with respect to x and y for both. And it's implicit because we're not explicitly solving for z here, right? Because z is part of that thing. And so when we do an implicit differentiation, we're actually doing it twice. We're treating z, so here's the thing. Treat z as a function. That's the idea here. All right, that's the big idea. We treat z as a function, x with respect to x, with respect to y. We treat those as, well, depending on which one, with respect to some variable. So here we treat z as a function. So WRT with respect to variable x or y. As simple as that. So let's start with this function. Let's do the first one. Let's do this first partial. So this is going to be with respect to x. So we take the derivative of x. We treat that as a variable, or y as a constant. This is 2x. This is 0. This is 5. Z is a function, so we take its derivative as well. This is 10. And then we have our z, right? Then we take its partial here, right? This is equal to 0. And then from there, I just switch it up, so I get this thing. This is negative 2x. I divide both sides by 10, so I get negative 2 over 10, negative 1, 5x. Oh, so I have an extra z somewhere. Right. So here I have to have a z. Okay. Yeah, I didn't know that one. Yeah, I have to have the z and then some partial. So I needed that z here. And so this is still 10z. Then I multiply everything by 5. Yeah, this is just x and then 5z. Right? And then that's it. That's how we solve for that. When we're treating this as some function, we leave it, right? Because this is basically, it's like a classic derivative. We take the derivative of the function. This was what's inside. So 10z, and then chain rule, which is just the partial derivative. And now we do the same thing when we want to find our partial with respect to y. Here we treat this as 0. This is for y. This is same idea, 10z, and then partial of z with respect to y. And then again, this is equal to 0. We say tan z of this, and then that partial is negative 4y. Then here we say that the partial of z with respect to y is just negative. I can just divide by 2 here. 3/5, right? 5z. So that's that. There we go. Okay. Nice. Nice, nice, nice. Okay, let's do one more because I feel like we could have done this better. So let me just go ahead and do one more. Just to get the feel of, oops, I think I included the answer, which is kind of messy. But anyway, I'll trust that I get this part. Okay, this one's a bit harder, I would say. But we're going to do it anyway. So here we have this. We want to find the implicit differentiation with respect to x and y. Z is a function here. So we do that same idea, where we treat z as a function with respect to some variable, either x and y, and then the other variable in here is a constant, right? Okay, so let's do it. So here we have derivative of e to the 7z. So that's just going to be, when we take that there, then we do a chain rule, 7z. What's the derivative of that? Well, that's 7z. 7 is just there. Z is just there. Over here, this actually 7, and then it's partial z over x. So here I could write this as something like this, maybe. This is equal to x, y, z. X is my variable. Y is a number that I just leave. So y is just there. And then here, x and z are the things I have to worry about. So how do I go about a 3-variable thing here? Because I have like 3 things to multiply. So I actually just combine one of them. That's what I would do. And this can be any. So what I'm thinking is that for this part, I'm just going to combine my y. Or I'm going to isolate my y because that's the number. X and z here should be together, right? The moment I take the derivative of this thing, this is just a product rule. So this, here this is just a 0. Because my y is some number. So that's just a 0. Here in this case, this is y. I leave my y there. And then here I do another, I do another one. I basically do another one here. So I have x, z, x, z. Then I get y here, I leave that. Here I get x, so this is 1, this is z. Plus x and z here, so this is x, partial of z, respect to x. Or respect to y in this case. No, with respect to x. Whoops. Respect to x. Yes. Okay. And then from there, I'm going to get some value out of it. So I get yz plus xy partial of z over x. So I think that was the tricky part here. Now if we were to combine everything, so 7, but really it's just derivatives. This is equal to yz plus xy. There we go. Now we isolate this z, right? Minus xy is equal to yz. Then from there, I can just factor out this thing. So I get something like this. Yz divided by 7e to the 7z minus xy. And that's my answer. Right? Cool, cool. Okay, so we did do all of that computation. It was a very messy one, I would say. Okay, let's do it again. This time with respect to y. Great. So again, we take the derivative of this thing. Actually, we get the same thing here. So now if we do this, we get its partial, but this time with respect to y instead of x. And then from here, I'm actually going to divide the task in such a way that my x is a number. And so what I'm going to do here is my x is a number, I take it out. And so I'm left with my yz here. And then from there, yeah, because my y is a variable, my z is a function. My x is just some number. From there, I could do... Actually, now that I think about it, I don't need to do a product rule here because I just leave the x be, right? So I'm just going to get something like x and then chain rule of this thing. Yeah, I just realized that. No, I'm saying chain rule. I meant product rule. That way it's quicker. This is just z, right? This is just y. Then this is partial with respect to y. And so I'm left with xz plus y, or plus, whoops, plus xy. Then my partial with respect to y. And now I have that thing. And so I just factor it out, right? So 7e, 7z of this thing minus xy of this thing is xz. Then from there, I just isolate my partial. So I would get something like xz over something like this. That's my answer. Oh, this is xz, by the way. Oops. xz. There we go. Nice. So the only difference is I changed my y to an x. But computation-wise, I think I'm good with doing this. Yes. Okay. Now, I think that's the basic idea. So I think I should be good. Second partial derivatives. So that one I just need to be really, 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 really careful. But basically, once I get the partial derivative, I just get second one with respect to something. I don't know what that is, but it's with respect to something. I'm not gonna go crazy over it anymore because I think I've studied enough to know what that is. And so we're good with that. Okay, I'm gonna put check marks on both of them because I know I'm good with that. So for my studying, I know I'm good with this part. So basically the idea, so just for a cheat sheet here, I guess the idea is, so based on what I just did, more or less, it's not even about contour maps. This one. So here, when we're being asked to look at something here, like a partial derivative, we're given some curve, check this out. Then when we're given some similar variables, let's say like f sub x, okay, let me see, or f sub y, then we basically are checking the slope of tangent line as it approaches the positive x or y axis. It's really as simple as that. When we're being asked to do something like fxx or fyy, here we're looking at concavity at that point. At that point. So what do I mean? So concave up is positive, while concave down is negative. That's it. And then we're looking again at fxy, which is just equal to fyx based on Claire-Knott's theorem. Claire-Knott's theorem. Here we're looking, let's say, from the first derivative. So from first partial derivative, say, let's say x. Move it a bit to y direction. Is it steeper? Right? If it's steeper in that direction as we move it to the y, like let's say this thing here. Oh, I don't have my cheat sheet. Is it steeper? If it's steeper, like let's say here we have fxy of 1/2. We look at my y, that's my y. I go down here. If I move it a bit here, is it less steep or more steeper? Here it's kind of less steep, and we know this is going in the negative direction. That's why it's positive. That's what I mean. So like to the, it's just an example. I'm trying to give an example. Positive y direction. Then here we're asking, is it steeper? Okay, let's say y, or let's say the first derivative is negative. So let's say if it's negative, check if it got even more negative. Basically, something like that. We're making some assumptions here. Let's say first partial is negative. It goes down. Is it steeper if we move it to y direction? Then it's negative. Else, it's positive. So there are a couple of, or there are different ways to go about a problem like this. And we just analyzed it. But yeah, it's really hard to kind of go through it one by one. Yeah, so that's the first idea of functions of two variables. And even for contour plots, it's really simple. What else can we say? When we see something like f of x, x is a variable. This basically means x is the variable, assuming we have x and y. Y is the constant, right? Nice and easy. If we have f sub y, well then x is the constant. Y is the variable. So something like that again. What else did we talk about? At least in that particular problem. Here we talked about, okay, fxy and then partial derivatives. So again, it really depends if we're doing a 2-variable or 3-variable. I'm gonna assume we're gonna do something 2-variable. I don't know, I just feel like it. And then here so for implicit differentiation, we basically treat z as a function with respect to, so cases where we have this or this, we basically treat z as a function And with respect to variable, and the other one is constant. Or it's some number, right? Okay, what else? Implicit, yeah, pretty much that's it, right? No issues here whatsoever. Okay, maybe okay, just to get back to 13.4 for a bit. No, I'm not supposed to do anything about it. But for 13.4, I want to specifically put the problem of this magnitude thing because I feel like it might come up somewhere. So something about force. So here probably put the problem with that F vector is m times the acceleration vector. But that's just for a 13.4 thing. And then this is for 14.1. Oh, I forgot that. 14.1 slash 3. That's that, pretty much. Now we move to, let's check off the list. We have a couple more. Now I move on to computing a tangent plane, which I think might be easier. So just some simple exercises we could try. Did we? No, I don't think we. So 14.4 is really just computing a tangent plane. And I think it was 14, week 5. So it's tangent planes and linear approximations. So if we just want some homework related to that, so something about computing. It's basically this thing, computing tangent planes. So what is that? Well, if we look at some homework here, yeah, because I know my professor is going to focus on the homework, so might as well use that, right? 14.4, more on computing tangent planes. We really just have to think about this formula and then just plug in. That's it. And I think it was some f sub x on that point. And then here we look at some slopes, right? There's a derivation of how this works. There's a reason why I memorized it. Because I remember posing a question here on what if we had infinite number of variables, then how many slopes can we find? What if we make a summation of that points, right? Because these are adding. But that's something I posed a while back, which I did not bother to check. Anyway, so let me go ahead and look at some problems here. I might just do 1 or 2-ish, maybe. Doesn't matter. So here, let's say this part. So it's really just finding an equation of a tangent plane at some specified point. That's the bottom line idea. That's really all we have to remember here. So here we have this function z. And then we want to get, oh, we also have a, b here. So here we kind of plug it in already, a and b. There we go. Then we just plug in the stuff that we know. So this is z, right? So z minus f of ab. Actually, you know what? Let's just plug in everything we need. F of ab. Wait, do I need to plug in the z as well? Oh, so I don't need to plug in the z. I just need to find the equation of the tangent plane. That's it. So f of ab in this case is f of 1, 1. In this case is square root of 1 times 1. It's 1, right? F of ab is 1. F sub x, right? Well, that one, we have to compute some partial derivatives to get it. So f sub x of this thing here is going to be what? Let me see. We do this. We bring it up front, right? We have 1/2 of this thing times the chain root. Oh, oops. This is 1 over 2 square root xy. Then we do a chain rule of xy. And so if we do a chain rule of xy, it's just going to be y. So I'm left with this thing. And so if I get the partial of that, well, then I have 1 over 2 square root 1, 1/2. I get 1/2 there. And then now I do f sub y. So again, it's this thing. But instead of y, I just change it to an x. So my f sub y at this point is 1 over 2 square root 1, 1/2 again. So I get 1/2 for both. And then, well, it's really just plugging in and stuff. So z minus 1, 1/2, x minus 1, 1/2, y minus 1. That's it. We're done. Okay, let me do another one just to, I don't want to do a complicated one because I'm trying to go over everything-ish. Oh, so there's also a linear approximation, which I don't think our professor will give in the exam. So I don't think that's something they'll give. But yeah, I almost forgot about that. Linear approximations, yeah. That one was a thing, apparently. So sketch path. I don't think no. Yeah, it was just some computing a tangent plane and then that's it. Then finding some derivatives to go along with it. Bottom line, that was it. Right? So we're not gonna focus. Yeah, let's not do it. I'll try to be as fast as possible with my review here. So okay, let's go ahead and look at. Let's do one more example, maybe. I just want to get the feel of how this looks like. So usually I do 2. The moment I mess up, I'm gonna do more. So that's all I'm gonna do here. Okay, let me do one more. So again, with finding an equation of a tangent plane. Oh, there's one about that. This is supposed to be straightforward, so I'm not gonna focus on it anymore. Yeah, let me just do this specifically. I could review for a bit if I had the luxury of time, but if I do have some extra time, I will try to go over some of these more in depth. But really, I'm just focusing on the key things I have to know. So here again, plug in, right? Z minus f of 1, 3 is equal to f sub x of 1, 3, x minus 1, f sub y, y minus 3. And I just need to fill in the blanks for these things. What are those? Well, f sub x, I take a partial. So this is, ooh, what is this? I treat my ln x as a number. My y as, oh, I treat this as a derivative. My y is just there. So y is just there. This is 1 over x. So I have y over x here. And so that means my f of x of this thing is just 3 over 1, which is 3. Now I have a 3 there. And then my f sub y is, so here I treat y as the variable, ln x as a number. So I basically just have ln of x. Here, I think I have a number, f of y of 1/3. This is ln of 1, which is 0. And so this is basically gone. This thing here is gone. And so I have this. And then for my f of 1, 3, I basically plug in the ln1 here. But ln1 again is a 0. So this is basically a 0. So this is gone. And so I'm left with z is equal to this thing. Done. Nice and easy, right? Okay, we do have some linear approximations, which I'm not going to go over too in depth anymore. Yeah, that's pretty much it for 14.4 stuff, right? So did we get that? Probably got most of it. Yes. Okay. So that's done. So for my cheat sheet for 14.4, it's really just computing tangent planes. That's it. And so we use that formula. You have z sum f sub, and then we take partials here. That's it. That's the whole idea of that. You just take partials and then there. Yeah, no biggie. Okay, and then for 14.7, which is a find and classify all critical points. So I think this was, I'm gonna combine this with, I'm gonna do this in the next video. I'm gonna take a break first. But basically, we find some critical points, homework 1 to 6, and then we do some applied maximum or minimum. That's similar to the homework. So really here, I'm gonna focus more on the homework than the old exams. Right. So 14.7 is more or less, I think this was like what, week 5-ish? Yeah. 14.7 is really more on maximum and minimum values in general. And we did talk about that in my calculus series. So pretty much it's just a review. So bottom line, max and min values, right? Okay. So I'm gonna stop the video here because I don't want, again, I don't want it too long, keeping it simple and clean as possible. But yeah, I hope you guys enjoyed, and I'll see you all. Let me just finish writing this. I'll see you all in the next video.